Given the root of a binary search tree and an integer k, return the kth smallest value, one indexed, of all the values of the nodes in the tree. So we're given this tree, right? We're given this tree, and we want to find the kth smallest value. K here is equal to 1, and since k is 1 indexed, that means that saying k equals 1 is another way of saying we're looking for the smallest value in this tree. If k was equal to 2, we'd be looking for the second smallest value in this tree. So we can see that the smallest value here is 1. And that is the output, or the value that we want to return from our algorithm, from our solution. So the simplest solution, simplest way to get that answer would be to traverse the tree in one of the 4 ways that you can traverse a tree. If you want to know the 4 ways to traverse a tree, check out the video linked now. So we'll traverse the tree in one of the 4 ways we can do it, and then we will process each node on the traversal and add it to an array. And we could traverse it. Let's say we traversed it breadth first search. So we did 3, and then we processed 1, and then we processed 4, and then we processed 2. After this process, we then need to convert this array, or we need to sort this array in numerical order. So we have 1, 2, 3, and then 4. And let's just say this new array is called R. Let's call it R. The way we'd get the value is we'd say k minus 1, because k is 1 indexed and arrays are 0 base indexed. So k minus 1 would give us the smallest element in the array, which is 1. However, even though this solution works, there is an easier way, or a more efficient way, to get the array. We can actually collect the elements from the tree in such a way that we don't have to sort the array after, because it will be sorted as we create it. We'll collect the elements in sorted order, in numerically sorted order. Okay, and numerically sorted, by the way, means numerically ascending in this case, numerically ascending order. So the way we can do that, the reason we can do that in the first place is because this is a binary search tree. And a binary search tree has the property that for every node, the elements in the left subtree are less than the node. So the elements in the left subtree are less than the node. And the elements in the right subtree are greater than the node. And we can see that here. The elements in the left subtree, 1 and 2, these are less than 3. And then the elements in the right subtree, 4, this is less than 3. So that makes this a binary search tree. Now, the traversal algorithm we can use is a depth first search traversal algorithm, and it's called in-order traversal. So we're going to traverse this tree in order. Okay, so we'll start at 3. And which means that we will process the node the second time we see it in the traversal. So let's go ahead and begin to traverse this tree. So we start at 3. It's the first time we see 3, so we don't do anything. Then we go to 1. First time we see 1, so we don't do anything. Then we go to 1's left node. It's null, so we go back to 1. That's the second time we see 1, so we add it to our array. Then we go to 2. It's the first time we see it. We go to 2's left node. It's null, so we go back to 2. That's the second time we see 2, so we add 2. We go to 2's right node. It's null, so we go back to 2. Third time seeing it, we don't do anything. Third time seeing 1, we don't do anything. Second time seeing 3, so we add it to the array. And then we go to 4, see it for the first time, go to 4's left node. It's null, we go back to 4, we add 4. Then we go to 4's right node. Then we go past 4 again. Third time we see it, doesn't matter, we don't do anything. And then third time we see 3, we don't do anything. So it's only on that second time that we actually process the node. And there we go. That's how we were able to collect this array here. And then if this array, again, if it was called R, we would then just, to get the value at the case smallest value, we do k minus 1, and this is what we return. Okay, so how can we implement this in code? Well, there's 2 ways to implement this. The first way is using recursion, and the second way is using iteration. Iteration, we'd be using a stack to keep track of the nodes that we have traversed, but I think the recursive solution is very elegant, so that's the one we're going to use here. The first thing we do is we would create an array. Create an array, or in Python, this would be called a list, and we'd set it to an empty array. Then we call a recursive function and pass in the root node and the array. So we'll just call this recursive function rf, recursive function. And we want to pass in the root node, and our new array, right? And finally, after the recursive function calls itself a bunch of times, there's a bunch of instances, so to speak, of this recursive function being called on different nodes in the tree. Our array will get filled up with all the nodes in the tree in the correct order. So then we would simply return, r at k minus 1. Okay, so what is our recursive function going to have inside of it? Let's build it out now. So this is our recursive function, this box. Inside of it, the first thing we're going to do is, remember, we want to do in order traversal here. So we're going to have if left node exists. Does it exist? Okay, then we will call this exact function again. So it's a function that calls itself, a recursive function. And then we want to, let's actually go through. So we start at 3. We call this recursive function. It says if left node exists. So does left node exist? Yes, it's 1. Okay, so we call the function again at 1. Does 1's left node exist? No, it does not. It's null. So then at that point, what would we want to do? Well, we would want to add that number to the array. So we would push or append, whatever language you're using, we would push that node's value. So we'll just call it NV, that node's value, onto the array. And then, so let's say we did that for 1. 3 has been called, so there's 2 recursive functions like in progress, so to speak. We've got 3 and we've got 1. 1 just pushed the node's value, which is this value 1 here, the number, onto the array, and afterward, well, we want to continue to traverse, right? So we want to go to 2. Okay, so if right node exists, we want to traverse it. So if right node exists, we want to call this traversal function. Even though we're calling it recursive function, we want to call this function again, okay? And when we get to here, it is going to start at the top. So now this is our third instance, so to speak, like our third instance of this function being called. And it checks if left node exists. No, it doesn't. Okay, then add the value to the array, and then check if right node exists. No, it doesn't. Okay, then we go back to 1, and this is called backtracing. When we go back from this node to this node, really when a recursive function pops back out, so to speak. That's called backtracing. So we backtrace out from 2 back to 1 all the way to 3. And now at this point, this is the only instance of the recursive function running, right? Because these 2 finished. They finished and we backtraced all the way to 3. So this is the second time we're seeing 3. We're at this point in the function. We have already done if left node. We went down that whole branch, that whole subtree, and now it's time to push the value onto the array. So we will push the value onto the array. That's 3, and then we'll hit the final bit of logic here. If right node exists, call this exact function on it. Oh, it does exist. Okay, so now we just opened up another instance of this recursive function. Now we've got 2 running, 1 for 3 and 1 for 4. 3 has not finished yet until 4 finishes. So we check with 4, if left node exists, if left node exists, run the function, but it doesn't, so we don't run it. And then we push onto our array the value 4. Then we check, hey, does right node exist? No, it doesn't, it's null. And we pass by 4, and then we pass by 3, and then we're done. So this recursive function instance had to complete before this recursive function at 3 could complete. And there we go. It finally finished. So all of that was happening inside of this call. We are calling this at the beginning of our code. This is the second thing we're doing. We're calling this function, and all of what we just saw, that whole recursive traversal process happened all inside of this function call. It was all triggered by that function call. And by the time this is done, by the time this is completed, our array, as we see, has been finished. It has been added up with all the values in numerical order. So then we can finally return array at k-1, and that is our solution. So what's the space-time complexity here? Well, the space-time complexity, they're actually both O of n. And the reason they're both O of n is, well, for space, we're creating an array that literally has n amount of elements in it. And then for time, we are calling this recursive function where essentially you can almost think of it as we're iterating through every element in the tree. We are traversing through every element in the tree. And we do it 4 times. We ended up calling that recursive function 4 times. 1 for 3, 1 for 1, 1 for 2, and 1 for 4, which ends up being 4 times. And there's actually one more thing worth mentioning. We continuously pass in our array into the recursive function. And you might think that that would create a new instance of the array and that the array would not be updated properly. Well, that would be true if we passed in a primitive type into the function, but we are passing in a reference type data structure. So this array, it points to or references space in memory. And you could almost think that that space in memory is somewhat global, and that the multiple instances of this recursive function will update the array, the same array. It'll update the same space in memory. So let's hop over to the code editor and solve this in both JavaScript and Python. All right, so the first thing we want to do is create an array. So we'll say let array equal, and we'll set it equal to an empty array. Then we want to call a recursive function. So recursive func, that's what we'll call it. And we want to pass in the root node and the array that we just created. Now we actually have to create that function. So we will say let, or rather const recursive func equals. So we're just using fat arrow syntax here. We've created a function, and this function is going to take in, a node and our array. And what we want to do is we want to say if node dot left, if that's a truthy value, then we want to call the recursive function and pass in node.left as well as array. Then we want to push onto our array the node.val. And finally, we want to do the same if statement, but using, or in regards to, the node's right node. Okay. And after all that's done, the last thing we want to do is return array at k-1. And that should do it. So let's go ahead and run that. Make sure that it works. That looks good. We'll submit it. Okay, great. Now let's go ahead and do it in Python. So in Python, we will do it in a very similar way, with the main difference being syntax. So we'll create this list. Then we will call our recursive function, so recursive func. And we'll pass in the root as well as the array. We want to create that function now. Pass in self. Oh, we actually have to call self on this. So self dot recursive function. And we will then pass in our root. So we'll just say node and array. Now we want to check if node.left exists, then we want to call the recursive function. So we'll say self.recursive func, and we'll pass in node.left. Then we will pop out of that if statement. We will push onto our array, or append. We will append the node's value. Then we will have another if statement for node.right. So for node.right, if it's true, then we want to call a recursive function on it. And that should do it. All we need to do then is return array at k-1. So very similar. Let's make sure that that works. Looks good. Let's submit it. Okay, great. And it works. And oftentimes it, won't have the best performance, yet the same solution can have vastly different performances. So here's the same solution with much different performance. And that's it. That is how to solve kth smallest element in a BST in both JavaScript and Python.